So far, we have been discussing about the fundamental aspects of photochemistry and several examples of organic organic phototransformation. We have studied the photochemistry of alkene, 1,4-diene, 1,5-diene, carbonyl compounds, alpha-beta unsaturated carbon compounds, beta-gamma unsaturated carbon compounds, cyclohexadienone, and some name reactions, and so on and so forth. So now we are just switching on to another aspects of photochemistry, which is photocatalysis. This is a heterogeneous photo-induced electron transfer reaction. When we have discussed the in the first lecture that the photolysis is the interaction of light, and when we shine light, molecule absorbs light, goes to an excited state, and then these excited states are high energy species, and they are short lived. They undergo the photophysical process like radiative, non-radiative process, or they can undergo depending upon the type of chrome 4 present in the molecule. And the and and in this photo excitation can be brought about by two ways. One is direct photolysis, otherwise indirect photolysis. Indirect photolysis is initiated by a sensitizer, and then which absorbs light, transfer energy, or transfer electron. When it transfers electron, then it is called a photo-induced electron transfer reaction. These photo-induced electron transfer reactions are again two types: homogeneous photo-induced electron transfer reaction and heterogeneous photo-induced electron transfer. So this is a so we also discuss some little bit about the heterogeneous photo-induced electron transfer. Now onwards, we are going to look at this in much more detail. Is a process called photocatalysis, in which the reaction is heterogeneous, and the this I mean the catalyst, the photocatalyst here is a photocatalyst is a semiconductor, and we know that the semiconductor is characterized by filled valence band and conduction band, and then if we shine light energy equal to the band gap energy, there is an excitation of electron, and these electron hole pair can be used for further reaction. This heterogeneous photo-induced electron transfer reaction involving semiconductor is started with a big bang with the last 20 years or so. Lot of work has been going on, and with the aim to it has been found that it may have a very good environmental application in the detoxification of wastewater. We know that the water coming from dye industry, coming from textile industry, coming from agrochemicals, pharmaceuticals, the runoff water, these industries, they use our pure water, and then they release highly contaminated water which contains a lot of organic pollutants as well as inorganic pollutants, and these pollutants are highly toxic, and some of them are highly carcinogenic as well. So this heterogeneous photo-induced electron transfer reaction involving semiconducting material can be it could be used for the degradation of organic pollutants in aqueous suspension. So that was the major aim in looking into these reactions in much more detail. As I have mentioned that the lot of our water system is contaminated. We can see is such a dark brown, the colored high material, water, our lakes and all are getting polluted, and even animals doesn't feel like drinking that. So it's a lot of toxic, used waters are contaminated in this, throwing in the water. You can see here this is again polluted water, is again highly contaminated water, and these comes from, as I have mentioned, from dye industry, chemical industry, municipal waste, also power plants and chemical spills also leads to these the accumulation of these toxic compounds in our environment. Not only that, the lot of in order to have a better quality and quantity of our crop, we use a lot of pesticides, and these pesticides, they of course they do their job. They can have we can have a better crop, we can have a bit more better quality and quantity of crop, but these pesticides are not they remain in the field, and then they during and they have a quite good solubility in water. So during rainy season or in the they just go deep into the water and contaminate our grounds water system, or they can seep to the groundwater, or they can just go to our rivers and canals. So our rivers and canals also gets contaminated with toxic organic the pesticides or herbicides which are used in the field. So this is another point of being concern to the society and regulating authorities all over the world. So the conventional method for wastewater treatment, we know that is a physical treatment and biological treatment and chemical treatment. Physical treatment involves filtration, adsorption, flocculation, but in this process we are not we are just transforming one pollutant into another pollutant. Say for example, the filtration leads to sludge, adsorption, filtration leads to the accumulation of sludge, and then evaporation leads to air pollution, and so on and so forth. And not only that, the organic compounds they are resistant to biological treatment, and hence the most effective methods, which are chlorine per stick acid, chlorine dioxide. But in these process it generates a highly chemical oxidants which generate harmful substance, which cause worse environmental problem as well. So these physical methods leads to transformation of one pollutant to another, and also accumulation of sludge and so on. These processes like ozonolysis, chlorination, and all those things leads to the generation of more toxic the oxidants, toxic species which remain in the water, and then they leads to the so in therefore there was a need for an economical and most viable feasible technology for the wastewater treatment, and then this advanced oxygen technology has come up of a great interest, in which the photocatalysis, just now I mentioned, it is an advanced oxygen process which receives a lot of attention for the purification of wastewater. And it could be a clean, safe, and highly exhaustive method, because we are using if we can use sunlight, then definitely it is going to be able. So most widely used semiconducting material are titanium dioxide, TiO2, zinc oxide, and so on and so forth, cadmium sulfide, cadmium oxide, zinc tin oxide, and bismuth oxide, and so on and so forth. These semiconductors, pure semiconductors, have been used for a lot of for the degradation of the heterogeneous photocatalysis for degradation or toxic organic and inorganic compounds. The basic principle involved in this photocatalysis involving semiconductor. Photocatalysis involving semiconductor as a photocatalyst, semiconductors such as TiO2 or ZNO as photocatalyst. So we know that considering this as a surface of the semiconductor, we know the semiconductor is characterized by filled valence band and a vacant conduction band. There is a band gap energy, it's called a Eg, and if we shine light in greater than or equal to this band gap, there is an electronic excitation from filled valence band to the conduction band, thereby generating electron and hole pair. So say TiO2 in the presence of light can generate electron hole pair, and then these electron hole pair, or in other words, it generates oxidation and reduction reduction and oxidation sites on the surface of the catalyst, and these and hence we can bring about redox reaction on the surface of the catalyst. So these reactions are surface reaction, heterogeneous reaction. They are not soluble in water, they are neither soluble in organic solvents, and hence the reaction takes place on the surface of the catalyst due to the generation of electron hole pair, or in other words, it generates electron which can be used to bring about reduction, and hole can be brought about oxidation. So in other words, it generates oxidation reduction sites on the surface of the catalyst, and hence we can bring about redox reaction, oxidation reduction reaction on the surface. So if we do the reaction, if these reactions are carried out in the presence of oxygen and carried out in the presence of water, so because this is the most environmentally friendly conditions, and even oxygen we can get it from air. If you bubble air which contains around 21% of oxygen, is more than sufficient to bring about these reactions. So oxygen pick up this electron, this oxygen on the in the environment, or in the, of course, when we do the reaction in the laboratory, the photoreactor is just we bubble air, and then it picks up electron and generates O2 dot minus. It is called oxygen plus electron. So one electron excess, so there are two electrons in one single bond, so you are just generating O dot and minus. We can represent this O2 dot minus. So this is called superoxide. And water gives an electron to hole. So water, when it gives an minus electron to hole, then it becomes OH radical cation. So after transferring electron to hole, water, it forms this one, and then this loses proton, and then minus H plus give rise to OH dot radical. So it's essentially what we get is O2 dot minus and OH radical. So these two species are highly reactive species, ultimately react with organic contaminants such as dyes, pesticide, drugs, and so on and so forth, which are present in the water system as a contaminant, as a toxicant, and it can bring about oxidation reduction reaction, ultimately leading to mineralization, carbon to carbon dioxide, and oxygen to carbon to carbon dioxide, nitrogen to ammonium salt, phosphorus to phosphate, and so on. So the end product is water and carbon dioxide. So in other words, what we are doing in this reaction is we are detoxification of water system, degrading toxic organic compounds to non-toxic organic compounds such as carbon dioxide in water. In other words, we call it as a mineralization takes place. So this reaction, heterogeneous photo-induced electron transfer reaction involving semiconductor as a photocatalyst has started with a great interest from environmental application point of view, in order to which detoxification wastewater and degradation of organic compounds in aqueous suspension. The main idea of doing these reactions was and if this reaction, if successful, then this could be a most viable and economical method for wastewater treatment. So for the last 2 to 3 centuries, this work is going on, and Professor Honda and Fukushima has initiated this reaction several years before, and a lot of work has been done, and still a lot of work is being done. We have also been actively involved in these reactions. So in coming few lectures, we would like to present some of our work and also the related work which others are doing. So basic principles I has mentioned is quite simple. Is quite simple in the sense that considering this as a semiconducting material. So I will just summarize the principle because it is very simple, and it can be visually explainable, considering this as a surface of the semiconductor which is characterized by filled valence band, a vacant conduction band. There is a band gap energy, and if we shine light, energy equal to or greater than band gap, there is an excitation of electron from valence band to conduction band. In other words, it generates electron hole pair or oxidation reduction sites on the surface of the catalyst, or we can bring about redox reaction if we do the reaction under inert atmosphere like argon or nitrogen. If we do the reaction in the presence of oxygen and water, oxygen is converted to superoxide radical anion and water is converted to hydroxyl radical in according to the mechanism which I have just now mentioned. These species are highly reactive and reacts with organic contaminants such as dyes, pesticide, drugs, leading to mineralization of this. Now, the for any application point of view, from the process, the optimal condition is to be determined, because what should be the which catalyst is very efficient, the type of catalyst, number one. Number two, the catalyst concentration, number three, substrate concentration, number four, phase pH, because if we consider this as titanium dioxide, this is a surface bond OH which can be protonated, deprotonated depending upon the pH of the reaction medium. And the some of the dyes which are, if they are, we would like to degrade, and we know there are some cationic dyes and there are some anionic dyes, and then some anionic dyes. So if the surface of the TiO2 is OH, or O minus, so depending upon which, so it is will be better absorbed with the cationic dye, and this as a anionic dye. So pH is extremely important in these surface reactions. So the from application point of view, it is always important to determine the optimal condition, which is the best condition for the in the laboratory scale, and then go to the pilot plant experiment for larger interest. So these are the different types of say for example, here this is mainly the TiO2. There are different types of TiO2, anatase or rutile, and then sometimes they are mixture of these. pH is important because for adsorption, desorption, substrating catalytic electron acceptor. The most main drawback in this semiconductor is the after generating electron pair is a back electron transfer, which is very fast, and also the energy gap, if it is Eg is band gap is very high, then we need UV light. So in order for commercialization, we need to switch over to visible light, and also by decreasing the band gap, and also to inhibit the back electrons. That is the second part of my lecture, but at present lot of work has been done by degrading a large number of compounds, by determining the degradation kinetics, by optimizing the condition laboratory scale, by studying a large number of organic pollutants. So, and then main aspects of what is the mechanism, because identification of byproducts is very important when we start with the degradation organic compound, because a big dye molecule cannot go to carbon dioxide plus water directly, but it goes via different intermediates. And these intermediates are identification of these intermediates are important in order to understand the mechanism involved in these reactions. The direct hole and so on and so forth. These are the few initial reduction, superoxide attack, and all those, because this is the reaction which takes place. And of course, later on, this will come to the second part. So as I have mentioned, we were also involved in carrying out these reactions, and we have done a lot of work by studying the degradation of a large number of pesticides, dyes, drugs, and so on and so forth. So some of the compounds which we have studied are the few pesticides such as Dinoseb. Dinoseb is a pesticide which has been used extensively in the fields for better crop and so this is another of course this is a organic pollutant. Chlorinated aromatic hydrocarbon is has been found to be. So these are the few pesticides which we have studied. What we have done is we have studied these reaction in the laboratory scale by in aqueous suspension using titanium dioxide catalyst and following the degradation by UV or HPLC and so on and so forth. Some other pesticide derivative which we studies is Dinoseb, Dinoturb, and then 2,4-dichloroaniline, 4-chloroanisole, some of the triphenoxy propionic acid, dichloroprop, and then acetamiprid, and some of the. So these are a few selected pesticide derivatives having different chrome 4, having chloro group, hydroxy group, nitro group, even alkyl group, and so on and so forth. And then and also we have studied the degradation of these compounds, and all these have been published, and they are all have been reported in the standard scientific journals. In addition to these pesticides, we have also studied the degradation of dyes such as acid blue 45. We have also studied xylenone orange, and this is also published in this journal. We studied neutral red, toluidine blue, and we studied also the chrysolidine, and then acid red. So these you can, if we can see here, these are azo dyes. A lot of azo dyes have been used for different application purpose. These are the we can say that the different class of dyes. We have a cyanine the functionality, and we also have a benzoquinone dye, and of course some chlorinated aromatic hydrocarbons. So we have been doing. So I've just given a list of compounds which we have studied. Now we'll see how we have studied this. What we have. We did the reaction in the laboratory in an immersion well photochemical reactor. In the very first lecture, we have shown that the photochemistry can be brought about by in a separate, in a different, in a very special reactor, because in order to avoid a lot of reflection of light, and so that more light is falling on the compound for better. So we can do the reaction in an immersion well photochemical reactor, which has a proper cooling and bubbling of air or nitrogen depending upon what type of condition we need. We do the reaction. We all set up the reaction and collect sample at different time intervals, such as when light on. This is the dye setup. HNU, light on, collect sample at different time intervals, at 0, 10, 20, 30, and so on. So this is the and we have monitored the reaction using UV spectrophotometer. This is the degradation of this particular dye in the presence of light, and this is the UV spectrum at time 0. You can see that the lambda maximum for this the absorbance is quite good. It is 1.5, maybe 1.7.5, 1.8, or 1.75, and so on and so forth. It's a quite colored solution, and then we do the reaction in the presence of in the titanium dioxide, aqueous solution of the dye, titanium dioxide, stirred, bubbled air, collect a sample, light on, mainly UV light, because titanium dioxide is had a large binding energy. We need a high powerful light, that is the UV light, and then we collect sample at different time interval. You can see that the measurement of UV at a different time interval, 15 minutes, 30 minutes, 45 minutes, 60 minutes, you can see the decrease in absorbance of the molecule, means the color of the dye is slowly the dye is becoming decolorization, or you can say that there is a loss of chromophore present in this dye material, which gives the color is going out, breaking down, so that the decolorization. The main purpose is to decolorize and also mineralize as well, because the sometimes it is some of the azo dyes, some of the intermediate which is formed is a toxic, the aromatic amines, which are highly carcinogenic. So identification of these intermediate products are also important. So this is a follow-up reaction of a photoreaction of a dye derivative such as acid blue 125 using UV spectrophotometer in a photoreactor, which consisting of an immersion well photoreactor, aqueous solution, light on, bubbling, air bubbling, quite stirring, collecting sample, centrifuging, and then following by UV. And we can see the decrease in absorbance, decreasing the color of the solution. I can show here, this is a different dye which has a blue, maybe acid blue here, it's a highly intense color, and then at different time intervals we can see is a highly colorless. So we can see that during the course of the reaction, the highly colored dye gets decolorized. This is a laboratory scale in 120 or 200 milliliter scale, in a immersion well photoreactor. The dye gets decolorized in the presence of photocatalyst, because the catalyst is important, light is important, because we have also seen a control experiment, as you can see here. This is another plot, just same as this one, but this is for a different compound, such as this one, acid AY29, this is acid yellow, and then this is lambda maximum at T0, and then you can see that different time interval there is a decrease in absorbance. And we have also, this plot shows that there is a change in the concentration versus time, and this is what we would like to concentrate here. This is a blank experiment. This is a blank experiment, without exactly all conditions are same except the light. So there is no catalyst is there, reactive, cooling is there, stirring is there, bubbling is there. So you can see that there is literally there is no change in the concentration of the dye when the light is off. So it is definitely this degradation is taking place, either this or this degradation or decolorization of dye is taking place in the presence of light. So we need catalyst, we need light, and then only this molecule gets decolorized from highly colored solution to decolorization solution. So this is another plot of showing the now, as I have mentioned, that the mineralization means we have also monitored degradation using UV and mineralization using TOC. TOC is total organic carbon. This is the how much organic carbon is converted to inorganic carbon. So this is the plot. We have this is a separate instrument to measure this, called total organic carbon analyzer. We collect same as the we measure the before the irradiation, we measure TOC, and at different time intervals we can see the decrease in this for TOC, decrease in TOC by TOC decrease. You can see that at time 0 it is this much, and then slowly at the irradiation time in 80 minutes the TOC has decreased to quite a low value, and it seems that the decrease in TOC means mineralization. How much organic carbon is mineralized from from organic carbon mineralized to inorganic carbon, TOC, total organic carbon, to IC, inorganic carbon. So you can see that these reactions not only degrading this is a degradation as we have followed by UV as here in this one, but this is the TOC. So these reactions are not only degrading the decolorizing, but it is mineralizing, as we can see from the decreasing total organic carbon content. Still a lot of work is done in this one, and then at present we just stop here and then continue on the next term. Thank you very much.